Hello, the purpose of today's video lesson is to talk about problem solving using tangent lines, lines tangent to the curve. So it's an application of differential calculus. So in this case, we're going to expect that the derivatives themselves should not be difficult, but it's what we do once we have the derivative that's going to be the challenge. So in the first example, we have an equation tangent to the curve. So this is going to give us a parabola at the point where x equals a. So there's some place where x equals a, and if I knew what x was, it doesn't matter, but I should be able to find the equation of the tangent line. Now they say, now that you have the equation of a tangent line for any value of x, find the equation of two tangent lines that also go through the origin. So the lines that we're talking about have to go through the origin and be tangent to a parabola. I need to see what this looks like before I can ever go any further. So on this graph here, we can see that from the origin to the parabola, we can see a tangent on the right, and there will be an even steeper tangent line on the left, and we could even get a ballpark sense, depending on how accurate our graph is, as to what values of x should be the correct values. For example, I think x equals 1 is probably going to be close, but we'll see. Anyway, we don't know exactly where this point is or where that point is, and so we use a comma f of a as a way of transcribing this point in function language. So instead of xy, it's a for the value of x that makes this spot happen, and f of a. Now there's a different a and f of a here. Now I chose a and f of a for both cases, which is kind of bad form. This could be b and f of b. But the fact is, I'm going to find both points using the same truth, and you'll see how that works in just a moment. Anyway, I can express the slope of these lines right here, this one and that one, in two unique ways. The first way is using the derivative, of course. So if I take the derivative function and evaluate it at a, then the slope of both of my tangent lines are going to be 2a minus 1. Now, the second way that I could calculate slope is to just use change in y over change in x. That is to say, here are 2 points. If you have the coordinates of any 2 points, you can find the slope and equation of the line that goes through those 2 points. So to find the change in y, I recognize that it's just f of a minus 0, and the change in x is just a minus 0, or a. Now f of a turns out to be a squared minus a plus 9, so I put that in a squared minus a plus 9, and then all divided by a. So this is the slope of both of these tangent lines, depending on the value of a, and this is the slope of both of these tangent lines, depending on the value of a. So they are both describing the same lines, and therefore the slopes themselves must be equal to each other. So I set them equal to each other. After that, it's a little bit of a mathematical, some algebraic skills. We can see a equals plus or minus 3. And then I do a little busy work. When a is 3, f of 3 is 15, so we have the point 3, 15, and a slope of 5 for the tangent line. So we use the point and the slope to find that y equals 5x. Here, again, f of negative 3 equals 21. The slope of the tangent is steeper because our second point was higher up, so we have a steeper slope, and it's, of course, negative. And using point slope form again, we get y equals negative 7x. So these are the 2 lines that will both go through the origin and be tangent to the curve. And just to make sure, I graphed y equals 5x, I graphed y equals negative 7x, and I graphed the given parabola, and I verify that at negative 3 and positive 3, 2 places where the tangent lines occur, y's are 21 and 15 respectively, and they do intersect the graph tangentially, so that makes me feel really good about the work that I did. Similar process here. This time, instead of going through the origin, I've got a point negative 2, 0, and the claim is there are 2 tangent lines to the curve there too. And what I can see, it's kind of hard to see in my graph, but there's going to be a tangent line here, which is the y-axis, and then there's going to be another tangent line here, which is going to be very steep, but I'm going to suspect a large positive slope for that number. It's not a perfect graph, but it gives me a sense of what I'm looking for. Once again, as before, I can find the slope in 2 different ways. One is I can use the derivative, so the slope of this tangent line and the slope of that tangent line are going to be 3a squared, depending on the value of a. Another way would be to use change in y over change in x, given the 2 points, negative 2, 0, and a f of a. So here again, 2 different slopes, set them equal to each other, solve, and I will have the 2 values of a that make the tangent line go through the point negative 2, 0. I found when a equals 0 or negative 3, and using these 2 points I can find the first line. Using these 2 points I can find the equation of the second line plus the slope to find the derivative, which the slope of the, or the derivative to find the slope. The slope of the tangent is 27, which I said was a large positive number, and that's confirmed by my graph, so I feel really good about this outcome. I find the rest of the equation, large y-intercept. In fact, we could see easily that if the slope's 27, we're going to go over 2, up 54. So everything jives with what it should. But just to make sure, I program both lines into the computer and show that they're both tangent to the curve that was given y equals x cubed, and they're both going through the point negative 2, 0. So again, satisfaction. Finally, same kind of problem for part C. The only difference is we're going to work with normals, not tangents, so we just have to take the opposite reciprocal of whatever slope we got. So instead of 1 over 2 squared of a, I'm going to say negative 2 squared of a, and that's going to be the slope of the normal that I'm looking for. As before, we can find slope using change in y over change in x, and as before, we set the slopes equal to one another, which requires a slightly more sophisticated algebra approach, but it's not that bad. It just requires the ability to collect like terms, factor common factors, and we get nice clean answers as a result. So to find the equation of y1, it's just y equals 0, no problem. To find the equation of y2, I need the slope of the normal, so I put in a equals 3.5 to figure out what the slope of the normal is going to be using my normal calculator right here, and then I get negative square root of 14, so I go through all this and I get the equation of the line there. This is the one that feels less trustworthy because it's got square roots of 14 in it, and the slope is square root of 14. That just doesn't feel right. But when I look at the graph, it does. Having x equals 3.5, I just eyeballed it and it looks right. So just to make sure, though, again, I go to technology. Notice I put in the slope or the equation of the line with no decimals, just exact terms like square root of 14. And here you can see it goes through the 0.40, and it is in fact normal to the curve right there. And of course, y equals 0 is 2 because it's perpendicular to the origin. Anyway, thanks for watching. Have a good day.